So our next speaker comes to us from the Netherlands, where he works at the National Post Office from the Netherlands. And he's an AWS hero and 12-time awarded architect. He will talk about integration testing, and it's something we don't hear so much about in serverless, and it's really, really essential. So without further ado, please welcome Luke.
Thank you. Can everybody hear me okay? I think so. All right. Awesome. Thanks for the introduction. Today, we will talk about confidently building cloud-native applications with serverless integration testing. And as the title implies, today's talk is serverless. But before we dive into the main topics, I want to quickly introduce PostNL. PostNL is the largest logistics company in the Benelux. In 2021, we delivered an average of 1.2 million parcels per day and over 8 million letters per day. And PostNL is on a mission to become a tech company. We're moving from being a logistics company that uses technology to being a technology company that builds products to do our logistics. We also have a full AWS serverless mandate, which means that any application built by our in-house development teams must be completely serverless. But of course, many, if not all, of the applications we build are mission critical. They control our sorting lines and our delivery routes. They power our customer-facing applications and websites. And if any of these applications fail, a large part of the Benelux might not be able to receive their books, electronics, or shoes. So reliability is extremely important to us, and one of the best ways to guarantee reliability is through automated testing. But the testing landscape for serverless environments is completely different than the landscape for EC2 or container-based applications. So my name is Luc van Donkersgoed. I'm the lead engineer at the PostNL integration team. I'm also 12 times AWS certified, and like some other speakers here today, also an AWS serverless hero. And I write articles about AWS serverless on bitesizeserverless.com. And today, I will talk to you about unit tests, why unit tests are important to guarantee reliability, but also why we can't use unit tests in a serverless environment. And I will talk to you about the solutions we came up with at PostNL to cover this gap. So first, let's take a look at the famous testing pyramid. It is used in classic software development to denote the difference between unit tests, service tests, and end-to-end tests. And one of the most important distinctions in the testing pyramid is that most of your tests should be unit tests. And that's because they provide a fast feedback, they run offline, they run very quickly, and they really provide granular insight into what works and what doesn't. In other words, they have a very short feedback loop. So here's an example of a few unit tests running on an application. They test happy parts and unhappy parts, and they run on a single function or maybe a small group of functions. And as you can see here on the slide, they run very quickly. In this example, 4 tests executed in about 0.02 seconds. So unit tests are fast, they provide short feedback loops, they offer great granularity, and they really verify the implementation details, the innards of your application. And that is also called open box testing. One step higher in the pyramid, we have service tests. And these tests also perform happy paths and unhappy paths, but contrary to unit tests, They run against a deployed service. They run in a deployed environment. And they really test only the integration points of your application. They test API endpoints or maybe SQS queues. So they know nothing about the internal workings of your application. And this is a closed box test. So the service being tested needs to be deployed before tests can run. The tests themselves are a bit more complex than unit tests. And the tests only test the integration points. And because of this, the feedback loop of service tests is a bit longer than the feedback loop you would see in unit tests. And the insights provided by service tests are a lot less granular than the insights provided by unit tests. Now, the top of the pyramid are end-to-end tests, and these really verify that multiple services work well together. So, for example, you can have a payment service and a loyalty service. And the test will execute a payment at the payment service and then verify that the loyalty points associated with that purchase are added to a user's account. Now, end-to-end tests are the most complex to build and maintain, and they take the longest to run. Depending on their complexity, they might run a few minutes, or maybe even up to an hour. And of course, they provide the least granular insight. So if any end-to-end test fails, a developer has to spend time to find out why it failed and to solve the issue. So, with the basics out of the way, let's take a look at what this means for serverless. Now, a commonly heard mantra in serverless is code is a liability. And of course, this is a bit tongue-in-cheek, but there is some wisdom in it. Because what we mean when we say code is a liability is that when AWS or any other public cloud provider offers a managed service, they will literally run and maintain it for us. They will monitor its performance, they will scale its underlying instances, and they will patch its libraries and operating systems. And when we write our own code, all of that responsibility lies with us. And this is true for network-based technology like load balancers or RDS, but it is especially true for serverless services like S3, DynamoDB, or SQS. I mean, who is still going to write their own queuing software when you can use the almost infinitely scaling SQS off the shelf? So, a non-serverless application might look like the one on the left. There's a load balancing component, a user registration component, a queuing component, and an email component. And all of these components are built and maintained by your developers. It is code that you own. But you also own the integrations between those components. Now, the same application in an AWS serverless environment might look like the one on the right. We have API Gateway for routing, Cognito for user management, SQS for queuing, and SES for email. And in this example, we built the application through infrastructure as code, and in the infrastructure as code and the configuration, the integrations between the components are the only pieces of code that you own and need to maintain. Now, of course, I'm comparing two extremes, but they do drive home the point I'm trying to make. And that point is that the code on the left has a lot of code that needs to be built and maintained, while the solution on the right does not have a lot of code at all. And the solution on the left has a lot of unit tests that can verify the exact functioning of your application, the implementation details, while the solution on the right hardly contains any unit tests at all. So let's look back to the three types of testing in the testing pyramid. There's unit tests, which provide fast feedback and granular insight. We have our service tests that test the integration points of your service. And we have the end-to-end tests that validate multiple services work well together. Now, in a serverless environment, there are really only a few unit tests anymore. Those that might verify the internal workings of any Lambda functions or Azure functions we might have. But it's really only a fraction of the amount of unit tests that you would have in a non-serverless environment. We do still have service tests and end-to-end tests, but again, these test the outside of the service. They know nothing about the internal workings of your application. And this leaves a gap in our testing coverage, because how can we still have granular insight, but now on a serverless application? This monitor is going off soon, so I have to tap it, otherwise I won't have my notes anymore. And we discussed, my notes are very important to me. So our answer to this missing piece in the testing landscape are cloud-native integration tests. And cloud-native integration tests really verify the individual components of your serverless application. So, for example, SQS, Cognito, or your Lambda function, or your API gateway. And we really recognize two types of cloud-native integration tests. The first verify a single service, for example, API gateway, and we verify that that service has been configured correctly. This API gateway might be configured with IAM authentication, so our tests should call the API gateway with an authorized IAM principal, and then verify that the call succeeds. Then we should call the API gateway with an unauthorized principal, and that should result in a 400 error and an access denied message. The second type of cloud-native integration tests verify that two components work well together. For example, we have SQS and a Lambda function, so our test should put a message on the SQS queue, and then verify that this triggers the Lambda function without a certain time threshold, within a certain time threshold, and verifies that the result matches our expectations. So cloud-native integration tests sit between unit tests and service tests, because unlike unit tests, they test an online environment, but unlike service tests, they verify the internal workings, the innards of the application. So the cloud-native integration tests are open box tests. So now that we know what to test, let's take a look at how to test these components. The first thing we need is the ability to call the specific components within our application. After all, we want to achieve open box testing with granular insight. So in the architecture on this slide, that means that this test will need to be able to call API gateway, to read CloudWatch logs, to invoke Lambda functions, and to read from SQS queues. And all of these actions mean that the testing service or the testing framework needs to know about all the individual components in your application. And it needs permissions to access those components as well. And this actually makes a very strong argument for hosting the testing framework in the same AWS account that hosts your service. After all, if we would use an external service, it might need very broad permissions to your application, and it might need cross-account or cross-internet access, which might be difficult to configure and maintain. Now, luckily, the AWS serverless landscape has a great tool for executing arbitrary functionality, such as tests, with a very granular permission system. And you might have heard of them. They're called Lambda functions. And we can actually use Lambda functions to call one service, call one component, and then verify that the result we expect is received in another component. For example, a Lambda function could call API gateway and then verify that the access logs for API gateway are present in CloudWatch logs. This would verify that access logging has been set up correctly and that the permissions for API gateway have been configured correctly so that it is allowed to write to CloudWatch logs. And now I'm hearing you think, okay, but that's a lot of custom code to maintain again. And weren't we working to reduce custom code as much as possible. And of course, you're right. But there are a few reasons why custom testing code is different from custom code running in your production systems. And the first is that that testing code is always bespoke code. There will never be an off-the-shelf solution that perfectly matches the use cases we need in our testing environment. The second reason is that there are very powerful and reliable testing frameworks that can do much of the heavy lifting for us. So for example, in JavaScript, you have Jest, and in Python, you have the Pytest framework. And the third argument why custom testing code is different from custom code in your production systems is that it is outside of the production loop. So customers will never interact with this code, so access patterns and performance for this code are less important than in your production systems. All right, so let's take a look at a test written in Pytest and running in a Lambda function. In this case, the use case is an API gateway configured with a request validator and a custom response. So our test should call the API gateway, then verify that the result matches our expectations. And as you can see, we do that through the AAA pattern. So first we arrange the test, we configure a valid payload. Then we act, which is calling the API gateway. And finally, we assert that the results match our expectations. In this case, a 200 response and a valid message body. Next, we also want to verify the unhappy path. So we have a test that looks much the same, but now we have an invalid payload. And we verify that we get the 400 status code and the expected JSON response body. Now, the first two tests validated that our API gateway as a standalone service works correctly. So now let's take a look at a test that verifies that two services work well together. In this use case, we want to verify that our API gateway always writes an entry to our access logs, both for valid requests and invalid requests. So we do the same as in the first test. We send a valid payload to the API gateway and then validate the result. But where in the first test we really looked at the response code and the response body, this time we will take the request ID from the response headers and use that request ID to look up the right access log entry in CloudWatch logs. And you might say, well, this looks very much like the first test that we had, where we called the API gateway with a valid payload. The only difference is now we look at CloudWatch instead of the response body. So couldn't these two tests be merged into one? But remember, we're looking for granularity. And by splitting this into two tests, we can pinpoint exactly what works and what doesn't. Now in this example, the Lambda function needs permissions to read from CloudWatch logs. And by following the principle of least privilege, that's also the only permission that this function will get. And that brings us to the next topic, which is scaling the tests. Because for any significant application, there will be dozens or maybe even hundreds of cloud-native integration tests. And if we would put them all in a single Lambda function, then that single Lambda function would need very broad permissions to your entire application, which would again break the principle of least privilege. But also, Pytest is a single-threaded application, so it could only execute all these tests serially, which could lead to very long execution times. Now, the solution is to create a testing function per tested component, also called the system under test. And this function would only need permissions for its own scope, and all the tests separately can be executed in parallel, which could lead to largely reduced execution times. Then these Lambda functions simply run the Pytest scripts that we saw earlier. So where do we store these tests? Well, much like unit tests, we include them in our application code. They're in the same code base. So in this example, you see a screenshot of my Visual Studio Code. And you can see we have a test folder, which contains our unit test, but it also contains the folder integration tests. And in that, we simply have a folder per testing Lambda function, much like any other Lambda function. And in that folder, you will find a number of classes or number of files prefixed with test underscore. And Pytest will scan these directories and will find these files named test underscore something and will recognize them as Pytest components. And as it discovers these files, it will open each of those files, and in it, it will find a large number of functions. And those functions are named test underscore as well. And Pytest will then recognize those as test cases and will execute them together as part of a test suite. So these tests will be executed by our Lambda functions. But there's more. Because we follow the exact Pytest conventions, we can actually use and run these tests from our local machine as well. And that might look a bit like this. So this is the exact output of Pytest running on my local machine. And these tests run on my local machine, but they test the components deployed in my AWS Sandbox account. All that it needs to do this is administrator access to that AWS Sandbox account, but since it's a Sandbox account, that's really generally not a problem. So let's see that in action. In this short clip, you can see the test running on my local machine. You can tell they're a lot slower than unit tests, but still they provide a very fast feedback loop and a very valuable result. And the tests being executed here look like the code on the left, and the architecture being tested looks like the diagram on the right. So now we've seen how these tests run locally. And that helps us run the test and verifying that everything we're building works, even before we're creating our first pull request for this code. But of course, we also want to run these tests as part of an isolated Q&A process. So we've seen how these tests are stored across a number of Lambda functions. So the next question is, how do we orchestrate these Lambda functions to run in parallel? Well, when somebody says orchestration in AWS, your first response should be step functions. So that's what we'll use. On this slide, you can see a state machine that has a single parallel state. And in the parallel state, it will execute every individual testing Lambda function. The parallel state collects the results of each function and will generate a test report based on those results. If any Lambda fails, for example, through an out-of-memory exception, a execution error, or a timeout, that exception is caught as well and included in the test report. Now, the main goal of these integration tests is to verify that new features we're adding work as expected, but also that as we're adding new features, they do not break any existing functionality. So a great time to validate that these goals are matched is at the time of pull requests. Because pull requests can run any kind of automation, including a deployment of our full stack to an AWS account, but also triggering the step function state machine that we saw on the previous slide. Now, at PostNL, we use GitHub Actions for our CI/CD processes. And as you can see on this slide, we have configured our GitHub Actions to first deploy the stack to an AWS account, then run the integration tests, and then wait for the integration test to finish. When all the integration tests succeed, the pull request can be merged. And when any integration tests fail, the pull request is blocked from merging, and the developer will have to fix it first. Now, the CI/CD integration does require a few additional steps being added to the state machine, and you see those at the top and the bottom. The step at the top of the state machine sets the GitHub pull request, the check, to pending, and the one at the bottom forwards the test report generated by the state machine back to GitHub. Now, a real-life example of that report looks like this. This is from our GitHub environment. And as you can see at the top, 23 out of 23 tests executed successfully. And in the middle section, you can just see the name of all those successful tests. If any test fails, the entire test is included in the test report, including the assertion that failed. And as you can see here in the zoomed-in area, the test, in this case, expected a 200 response from a Lambda function, but it got a 500 error code. And in this case, that was caused by an updated dependency, which is exactly the kind of error we're trying to catch with our unit tests, integration tests. So let's recap what we discussed today. First, the old testing pyramid heavily relies on unit tests. But in our serverless applications, we're reducing our custom code as much as possible, which also leads to a reduced importance of unit tests. But that leads to a gap in our testing coverage. This gap is filled by cloud-native integration testing, as shown on this slide. Now, cloud-native integration tests are best run in the AWS account hosting your service, which allows the test to directly interact with the AWS services under test. Lambda functions and a testing framework like Jest or Pytest allow us to really focus on the details of the test, while the heavy lifting is done by the framework. Orchestration of the test is achieved through step functions, and we integrated these state machines into our GitHub Actions pipelines, but with a bit of custom code, you can integrate this pattern into any pipeline, including GitLab or Jenkins or even Azure DevOps. And with these tests in place, our serverless mission-critical applications can be delivered to production both quickly and reliably. And that allows us to deliver your parcels both quickly and reliably. Thank you for your time, and enjoy the rest of the day.
Thank you so much, Luc. That was actually very, very enlightening.
Thank you.
Any questions? 1, 2, 3, 4, 5, 6. Okay.
Gagné.
What time is it? Yeah.
Hello. Thanks. This is great. So I guess for all of your test builds, you're just completely using Lambdas?
I'm sorry, couldn't...
Yeah. For all of your test builds, like so all of the tests in your system, you're just using Lambdas? Is that what I understand?
Not one Lambda per test, but one Lambda per tested component. So if we have API Gateway, for example, we might have 20 tests, and those are included in a single Lambda function. But then if we also have SQS, we have a second Lambda function, which might also contain 20 tests. So those two combined would run in parallel, but the 20 tests would run serially.
Right, and I guess that means that for every end-to-end test, or like every integration test you have, you would potentially rebuild your entire whatever, like all of your serverless Lambdas, they would exist separately?
Yeah, we use this in combination with a microservices architecture. So the microservice itself should be small. It's a microservice. So the amount of tests should be limited. But yes, we deploy the entire stack, including its tests, for every pull request.
Cool. Thanks, Ben.
Welcome.
Thank you. Please keep the questions short, as Mr. did. No, it was good.
Mine is really quick. Thank you so much for the conference. What about the cost? I mean, like, if you deploy all your tests within Lambdas, are you not like also augmenting, by a ratio the cost of the infrastructure? Because now you're running that code not in a single machine, but in many Lambdas. It's like, what about the cost of the infrastructure?
Well, I think quality is allowed to have a cost. So let's put that first. But then again, we're really talking about like single euros per month for this system, because it's all Lambdas and step functions. And they only run as pull requests. So let's say we have 10 pull requests a day, which would be a lot. That would mean that every Lambda function is invoked 10 times a day. Well, I think you know the pricing of AWS Lambda. That won't cost much. So that's not really a concern.
Great, thanks. Yes?
Thanks for your great talk. If I understand well, you run the integration test for every pull request you make. So if you have 10s or 20 pull requests, you're running on 10s or 20 isolated environments. Is that correct?
That is correct. So we deploy the service we're testing under a dedicated stack with a dedicated name. So if you would have 10 pull requests open, that would mean that in one single AWS account, we would have 10 separate stacks deployed at that time.
Okay, I see. Thank you.
Nice. Quick and concise, thank you. Very good.
Thank you for the presentation. Last one?
Two last ones, yeah.
Okay.
Yes, you guys.
Would you consider the CDK unit test as a good alternative to cloud native integration test to check, like, for example, that API gateway has a log group in which it can send logs and has an IAM policy that allows put logs, for example?
Yes and no. So we use those the CDK tests as well, the assertions, to verify that the components that we expect to be there are there, and also that they have the properties that we expect them to have. But, well, there's this entire debate between local testing and online testing, right? And I'm really in the camp of you can't verify offline if it will work in the cloud, because there are simply more moving parts, more additional components. So if we really want to verify that it works in the cloud and has been configured correctly, we use the cloud native integration tests. But if we want to verify that the components are there, we use the assertions in the CDK framework.
Hello, thanks for the presentation. I'm just here.
I see one more question there and then one more question there.
So a lot of my questions were already asked, but I have one last one. What's your strategy for like asynchronous calls? So how do you check that a message has been sent to Eventbridge or an SQS, for instance? Do you wait? And just a last question, how many bugs did you have last year?
Okay. I'm sorry, I didn't get the second question. How many bugs? Okay. Well, 0, of course. We catch them all with our tests. So your first question... Oh, yeah, yeah, so that's actually a complex topic. I could do a separate talk about it, but what you need is a test fixture. And a fixture is really like the literal word fixture in machine working, is you build a sort of wooden or steel construct in which you place the thing you want to test. And you need something like that for your asynchronous solutions as well. So you have your fixture, which might have, for example, a testing queue or a testing log group or a testing API endpoint, and you place your application in that fixture, and then you can read from those fixture queues, those interfaces, if you got the responses that you expect. But I must say that's really one of the most cumbersome things to build around this solution, and really something you need to invest in if you want to achieve this level of testing. One last question, I think. Let's see, one more.
Yes.
Microphone is on the way.
I just wanted to know, what about the data you're testing on? Are you like closer to the production data, or do you like use a lot of mocks just to run your tests?
Yeah, it's not exactly mocks, but we do have like sample data that we test with. We don't at this point use production data or anonymized production data. We really try to define the test cases that we want to test and write our own data for it, our own payloads. And then if at some point we find out there's a situation that we didn't cover with our tests, we write an additional custom test to add to the framework. But we don't use production data as of now.
All right, that was very clear. So thank you, Al. And
you're welcome.